Hello, everybody. Welcome to the experimental design lecture related to the artificial intelligence engineering in the Faculty of Engineering of the Autonomous University of the State of Mexico. Today it is Monday, the 6th of April, 2026, and we are going to start our lecture. So let me share with you my screen. Okay. Okay, so let us start. I am going to open this new file, save as. I'm going to put experimental design lecture 6 April 2026. Okay. I am going to put it here in download. Save. Okay. Okay, so let's start. We are in the experimental design. This is the program in the Bachelor in Science in Artificial Engineering. We are going to have this 180 minutes. Language is in English, and the date today is 6th of April 2026. Perfect. So let's put this in bold. Okay. Here. Okay. Today we are going to start talking about our second subject. In particular, we are going to study the following topics. So the topics for today are 2.1, which is related to exploratory data analysis. Here the idea is to, the objective is to perform a comprehensive exploratory analysis of experimental data using descriptive statistics and visualization techniques to detect outliers, assess normality, and identify patterns before applying formal inferential models. Okay, the second topic for today's class, it is called statistical parameters. And here the objective is to define and calculate critical statistical parameters such as example given, the mean, the variance, the skewness, and kurtosis, to quantify the performance metrics of hardware components and integrate these parameters into artificial intelligence validation protocols. Okay? And last but not least, 2.3 is related to the sampling theory, and the objective here is to apply sampling theory to experimental data acquisition, understanding the law of large numbers, which acronym is LLN, and the central limit theorem, which acronym is CLT, to determine representative sample sizes for artificial intelligence model validation. Okay, these are the three topics that we are going to study today. Okay. And let us relate it with the mousetrap exercise that you carried out during the holidays. We are going to talk about this experiment later on, but for the time being, let us put the following. So, in the context of the mousetrap card design challenge, do you remember? The point is that you are not just designing a car. Let us put it here. You are not building a car. You are designing an experiment. Your goal is not to get the longest distance, just by luck, but to understand why it happens, why this car is getting the longest distance, okay? That is the idea. So this is a very important thing. Let me underline this because it is the objective of this part. Here I have one question. The question is, what happens if you only test good, let me put it like this, good looking designs? So this is first question. Exercise. First, what happens if you just test good looking designs? Second question, what are the important factors in the mouse trap car design? What are the important factors? Which one did you consider in your teams? Okay. What variable have an impact on traveled distance? Let's put what variables have. And fourth question, let us put here for question. And which factor or variable, if you want, has the strongest effect on the distance as well? Okay. So I am going to copy this in the chat. And I am going to put you in teams, random teams. Perhaps you are going to share the team with some of your classmates. Perhaps you are going to be with some new people, but it doesn't matter. The point is that what I would like you to do is to talk about the answers to these questions, please. So let me break down the class in groups. So how many people are there? Okay. Okay. I am going to give you, it is 4:30. You are going to have 15 minutes. So at 4:45, we are going to discuss the answer to these four questions. Okay. So I am going to put you in some teams. So please join your teams, please. Okay. Daniel, are you there? Okay, guys. So let us discuss every question. So let me see. So the first question is, uh, what happens if you only test good-looking designs? So, what was your answer to this question? So, team number one, what was your answer to this question?
Am, Alex, ¿puedes pegar las respuestas en el chat, porfis?
Yes, if you please can put the answers on the chat, that will very helpful, and we all can read it.
Es que las anotamos en otro lado.
Ah, okay. Okay. So I already have team number one, Edgar Alexander. Uh, Edgar, could you please tell us about the answers?
Yes.
So what happens if you only test good-looking designs?
Our opinion is that you don't know the physical limits of your system and you ignore a fatal error.
Okay, yes, it is okay. And the second question, what are the important factors in the mousetrap car design?
Yes, we identify the independent variables, the effect, like the weight, arm length, strength. Um,
Okay, these are uh, three or four of these variables. And question number three, what variables have an impact on traveled distance?
yes, we identify variables like the city wheels, the string, and the arm.
Okay, and finally, which of these factors has the strongest effect on the distance, according to your experiment?
Yes, we think that the arm is the main thing because
The-
it connects the axle, the nylon,
uh-huh.
make it. makes it move forward to generate traction.
Okay, okay, perfect. Okay, thank you so much, Edgar. Now let us move on to the second team. David Nava, can you please tell us about your answers, please?
Yes.
So the first question is what happens if you only test good-looking designs?
Uh-huh. Testing only good designs creates a narrow data range without extreme values, because this prevents real learning and causes AI models to fail in the real world due to dangerous extrapolation.
Okay, perfect. What about the second question? What are the important factors in the mousetrap card design?
Yes. The most important factors are the independent physical variables you can manipulate. These typically include the lever arm length and the
Mm-hmm,
strength length,
mm-hmm.
wheel diameter, axle thickness, and the total chassis width.
Okay, perfect. And what variables have an impact? Did you explore all of these or just you play with some of them?
Okay, we think in torque, friction, and energy efficiency, because these impact distance most, but specifically lever arm length and the string length and the chassis weight determine if energy translate into forward movement or wasted wheel spin.
Okay, perfect. And finally, which factor has the strongest effect?
Mm, the lever arm length usually has the strongest effect
Oh, okay.
because it dictates the torque profile,
Huh?
and if too short will spin out. If too long, it lacks force.
Okay.
Optimization is critical.
Okay, perfect. Thank you very much for your answers. What about the other two teams? Team number David, were you in team number two? Is it okay?
I don't know, teacher.
Ah, okay. Well, there are two teams missing. What were your answers? The other two teams. Can you please put it on the chat as well? Okay. Okay. So, okay, thank you so much, Alan. Can you tell us about your answers, please?
And yes,
Okay, so the first question was, what happens if you only test good-looking designs?
uh, well, I identified that the most important fact, no, this incorrect. We observed that when we only tested good designs, our results become biased
Mm-hmm. Yes,
because
yes, yes.
we ignored unsuccessful case. As a result, we were not able to identify the system limits,
Okay.
which led to incomplete understanding and less reliable conclusions.
Okay, perfect. The second question, what are the important factors in the mousetrap card design?
The most important factors in the design are the lever arm length, the string length, and the chassis weight. Science all of them directly influence how energy is transferred and how efficiently the car moves.
Okay, perfect. Question number three. What variables have an impact on traveled distance?
The travel distance is mainly affected by the lever arm length,
Okay.
string length, and chassis weight because these variables determine the balance between torque, friction, and energy efficiency during motion.
Okay, perfect. And question number four. Which factor has the strongest effect?
The lever arm length has the strongest effect on the travel distance as it controls the way energy is released and therefore has the greatest impact on the overall performance of the car.
Okay, thank you so much, Alan, for your answers and the team. And there is just one team missing. Can you please put the answers to the four questions as well on the chat, please? Okay, so thank you so much, Angel. Can you tell us about your answers, please? Uh, what first question? What happens if you only test good looking designs?
Yes, teacher. We were talking about that the model. Well, we won't know the real limits of the model because we just testing good designs. But if something goes wrong, uh, the experiment will fail probably.
Exactly.
Um, well, that's the first answer.
The first answer, correct. Thank you so much, Angel. Second question, what are the important factors in the mousetrap car design?
We could identify some of them, like the wheels, the chassis weight,
Uh-huh,
the arm, the length of the string, so
uh-huh.
on.
Okay. Question number three, what variables have an impact on travel distance?
While we were doing the mousetrap car, we noticed that the chassis weight and the lever arm length were the most important fact variables
Uh-huh,
in
yes.
in the experiment.
Okay, and finally, which factor has the strongest effect?
The level arm length.
Okay, thank you so much. Okay, so thank you everybody for your participation. Let's continue. So first, let us analyze this. So first, we have to look at the, I am going to put here, let me use Roman numbers. No, first. Uh, 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 uh. Okay, so we have to understand the system. So in terms of system understanding, the variables, okay, that you already have mentioned include the following. Let us put some bullet points. For instance, you already said that the level arm length, uh, also important is the string length. Perfect. You also have to play with the wheel type. You can play with that variable, and the weight of the chassis, right? You mentioned that, and all of them have an impact in the response variable, which in this case is the distance traveled. You are going to measure that in meters, okay? So that is the first point. So let us suppose the following. I am going to put here a table in the screening design. So let me insert a table. Which is okay. So here we are going to put the experiment number. Here we are going to put the lever, and we are going to measure that in centimeters. Then the string as well, the length of the string in centimeters. And let us think that these are all the variables that we are considering in this experiment, and we are going to measure the distance, okay? Okay. So in the first experiment, imagine that you have a lever arm length of 10 centimeters, and the string has got 50 centimeters. And when you run the car, it goes far for 4.2 meters. Okay, that will be the first experiment. Then imagine that in the second experiment, you have a lever of 30 centimeters. Now you still have 50 centimeters in the string, and now the distance is 6.8 meters, right? In the third experiment, you have again 10 centimeters for the level arm length. Now you have 150 centimeters of the string, and now the distance is the 9.1. And finally, you have a fourth experiment where you have 30 centimeters in the lever. You have 150, you can get a distance of 9.5 meters, okay? So what we can see, that the factor that has the strongest effect on the traveled distance is as you already mentioned, you can see that if you have a short lever arm, well, the distance is certainly short, right? In this case, when you have 10 centimeters, you can reach 4.2. If you again have 10 centimeters, in this case you can reach 9.1. But if you increase this length from 10 to 30, you also increase the distance, right? Now you have, instead of 4.2, you now have 6.8. And instead of having a 9.1 in this part, you now have 9.5. So indeed, the lever arm length has a strong effect on traveled distance. Okay. And yes, there are some interaction, right? Because if you modify the string, you increase the distance as well. If you have 50 centimeters in the string and 30 in the lever, you can improve the distance. And if you have 150 centimeters in the string, again, you have a new improvement, right? Okay. So if you just look at this data, you can have some initial conclusion, okay? This is the screening design. So in the third place, let us put here, in the third place, let us carry out the exploratory data analysis, which acronym is EDA, okay? So before optimizing, we must understand the data behavior. So how is it behaving? And we can look at some out layers, that is the name. So let me put some bullet points. So one out layer that would be that if a car goes extremely far. So if suddenly you have these measures, right? 4.2, 6.8, 9.1, and 9.5. And suddenly a car goes as far as 20 or 25 meters. That is an outlier, right? Because it is not within the range of these values, okay? That could be by luck. That could be by luck, or some strange variable is influencing this distance. For instance, imagine that there is some inclination, right, in the surface where you are putting the car, and suddenly, well, the car goes very far away, okay? So this measurement error or lucky run. So an outlier is that data that is out of the expected range, okay? What else can we say here? The skewness, it is related. For instance, either you could have many short distances and few long distances, okay? That is the point of skewness. And let us see now at the You can also analyze one pattern. So increasing the lever improves the distance. So you can identify one pattern, okay? You can see that if you increase the length of the lever arm, the distance also increases, okay? But up to a point, up to a point. I mean, this is not like to the infinity and beyond. No, there is a limit. You increase the lever arm and the distance improves, but there is some point where you are going to increase this lever arm and the distance is not going to improve anymore. Okay? So let us see a numerical example here. In number 4, to illustrate these concepts. Numerical example. Okay, I am going to put here a table as well. Okay, I am going to put here the lever just to isolate this variable, just the lever, okay? And I am going to record the distance in meters, okay? So let me put this format to this table. So imagine that you have a lever of 10 centimeters and you record the distance of 4.2. Now, I double the length of the lever arm from 10 to 20 and you improve the distance and now you can record 6.5. Okay. Then I increase from 20 to 30 and you reach 9.5 meters. So you are identifying here a pattern. If you increase the length of the lever arm, the distance also increases. And finally, you have a 40 centimeters and the result is just 9. Okay, it decreases again. How can you interpret that? Let us put here some bullet points. Okay, so increasing the lever arm translate into improvement. But there is a peak, there is a maximum. This is the peak is the optimal point. And then when decreasing, you have inefficiency. And that represents this is a nonlinear behavior. This is a non-linear behavior. One thing to remember is that more is not always better. Okay? This is an important thing to remember. More is not always better. Let me illustrate this in the MATLAB. Okay. So here I am putting the lever arm, the length, which is 10, 20, 30, and 40. Okay, it is just the table that I wrote down in the Word document. Okay, and the distance recorded is again 4.2, 6.5, 9.5, and then 9. So I am going to run this script. And it is busy. Look. Mm, let me copy this figure. I am going back to the MATLAB, so let me just put this in the Word. Okay. Here. Here is the figure that we can have with the MATLAB. Let me copy again the figure because I think that it is not clear here. So I am going to get rid of this and put it again here. Okay, look. This is the data for the experiment. You are just considering the lever, okay, the lever arm. So 10, 20, 30, and 40. And these are the distances 4.2, 6.5, 9.5, and 9.0. Okay. If you put this in this graph, you can see that for 10, you have 4.2. Here it is this blue dot. If you have the 20 in the lever arm length, you can reach a distance of 6.5. If you have 30, you can reach a distance of 9.5. And here, if you have 40, the distance is only 9, okay? And there is one point here, which is the optimal, and that is the maximum. So if you see, this is not a line, a straight line, but it's a curved line, okay? It is a second degree equation, right? This is a curve, okay? So what is happening here? That not necessarily the more lever arm you have, the better the distance. Not necessarily, because there is some point when you reach the optimal point, the maximum, and then it will start decreasing. Okay, it will fell down this this distance. Okay, imagine the following thing. Um, for instance, if you are working in a team, if you have 2 or 3 people, they can work very well together. 2 or 3 people work very well. But what happens if you have 5, 6, 7, 8 people in one team? When you have so many people in one team, the productivity decreases. Why? Because some of them are not going to work. Some of them are going to be very lazy. They are just going to be sleeping. Instead of working, they are going to sleep because there are so many people in this team that they cannot agree in the task. So they are going to lose productivity because there are so many. So what is the optimal number of members in a team? For instance, in one of these classes, like the one of experimental design, I think that with 4 or 5 people, you are okay in the teams. But what happens if for instance, I propose a team of 10 or 15 people in one team, they are going to lose productivity, right? Because it not necessarily the more members the team has, the better the productivity. Not necessarily, okay? So that's why this statement is very important. More is not always better. And this is happening in this very experiment, okay? Let me put here some results. I am going to copy these results in the Word. So here we are. Okay. So here with this table, we can see the following results, right? This is the graph, okay? This is for optimizing, right? The mouse car trap optimization. And look, the mean distance is 7.30. Okay. So let me put here a division. Okay. And here. If you estimate the mean of these values, that means that you add up all of these 4 quantities and then you divide it by 4. You can get this result, 7.30. That is the mean distance with this data, okay? The variance is 5.99. The standard deviation is 2.45. And here the skewness is minus 0.39. When you have a negative skewness, it means that the data is concentrating at the right of the graph, okay? And if you have a positive skewness, that means that the data is concentrating at the left of the graph, okay? And the kurtosis, that measures if you have a sharp, if you have a sharp in the graph. If kurtosis is greater than 3, that means that it is a very sharpened distribution. If you have less than 3, the kurtosis, that means that it is very you don't have this sharp, okay? It is a low figure. So let me put here. Here are the interpretations. For instance, the mean is the average performance of the mousetrap car. The variance means if you have high variability, the design is unstable and inconsistent. The skewness, a negative skew, few low performance runs, short distances. So just in this case, just one, 4.2 was very low. And the kurtosis means that the data is flat, It is not a sharpened shape, but it is flat, okay? And what is the optimization? Well, in this case, if you have here 37.43 centimeters of lever arm length, you will get 9.26 meters, which is the optimal distance. Okay. Well, let us play a little bit with this thing in the MATLAB. So I am going to stop sharing this part. Okay. Let me show you some things about these shapes, okay? For instance, imagine that I have 500 different measures of any variable. Here I am going to run this routine with random numbers, okay? These random numbers are normally distributed. So look what happened. So imagine that I have 500 mousetrap cars, and I measure all these cars. So let me put it in these terms. So here I will call this variable datos, and imagine that I have, for instance, the first car has 4.2, the second 6.4, the third 3.9, then 7.7, and so on. I have all these different measures, right? 9.2, 8.3, 4.9, 9.6, 5.7, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 7.3. Okay? So let me see. Okay. I am going to put this on the Word. Example. And I am going to copy the results. Okay? And we are going to interpret that together. Okay. Okay. Let me share the Word. Okay. Here are the distances. And I am going to put here the results. So I am going to put example. And I'm going to put here the results. here. Okay, so let me put here. Okay. Here we go. These are the distances. I just proposed this. I just invented these values. But here is the statistical analysis, okay? So in terms of the central tendency, the mean or the average is equivalent to 6.62. That means that if I had carried out these 10 experiments with 10 different mousetrap card designs, on average, they will have go 66.72 meters away, okay? The median, which is the midpoint, is equivalent to 6.85. And the mode, which is the more frequent value, corresponds in this case to 3.9, okay? So in this case, the interpretation is that if the mean is greater than the median, there is a right skew, okay? Now, let us see at the second part. So I am going to put this together. This is the interpretation. Now, the dispersion. In this case, the variance is 4.11. The standard deviation is 2.03. This is the square root of the variance. And the interpretation, it indicates how far the data points are from the mean. If the variance is a large number, that means that the data is very far from the mean value, okay? If it is a small variance, that means that the data is not changing so much, it is close to the mean value. Okay, let us now talk about the shape, skewness, and kurtosis. Skewness in this case is minus 0.02. That means, because this is not greater than 0. So in this case, if skewness is greater than 0, it indicates a right leaning tail. But in this case, it's negative, so it indicates the opposite, which means that it is the left leaning tail. Okay, and kurtosis, the value is 1.68. That means that in this case, it is not greater than 3. So it is not a pointed shape, but it is a flat shape. Okay, it is like a sandwich. It is flat. And finally, the normality. In this case, this data seems to be normal distributed, and well, it has got the bell shape, okay, the bell shape. So I am going to put this example here, and I am going back to the MATLAB. Okay. So let me okay. I am going to run here. Okay. So look, I am going to run Mm, 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 mm. The figures, okay. Look, when I have a bell-shaped, a bell-shaped distribution of data, that can be considered as a normal distribution or Gauss distribution. Okay. And here you have a QQ plot where the red line represents the perfect normal distribution, and these blue dots correspond to the data that you actually have, right? So if I plot this shape, you can see that in a normal distribution, the mean and the median are equivalent. They are the same, practically the same. They too overlap in this graph. Okay, they too overlap because this is a perfect normal distribution practically. And in this plot, you can see that yes, indeed, you have this 45 degrees practically, okay? A straight line where all your data, the blue points, correspond to this red line, which is the theoretical, okay? This is the theoretical, and this is the data that you already have. So in this case, let me copy this figure in the Word. Mm, mm, mm. Share Word here. Word experiment here. Okay. So more examples. I am going to share with you this file at the end of the lecture. Okay. So here is an example, and let me put the interpretation of this. Okay. I am going to copy from MATLAB. Here we are. Okay, here is the interpretation. Okay. More examples. Okay. So for this case, this particular case, the central tendency, the mean, corresponds to a negative value of minus 0.02. The median is practically the same, 0.03 negative. And the mode corresponds to the value of 0.3. Okay, that is the central tendency. So in this case, in the interpretation, if the mean is greater than the median, there is a right skew. In this case, it is not happening. So it is centered just in the median value. Okay. What about the dispersion? In this case, the variance corresponds to 1.01, and the standard deviation, it is 1. How do you interpret this? Well, that indicates how far the data points are from the mean. So they are very close from the mean, just the variance is 1, okay? Do you remember in the previous example, the variance was 4.11. The data is very far away from the mean value. In this case, just 1. What about the shape? Skewness is 0.05. This case is positive. It means that there is a right leaning tail. So it is a little bit to the right, okay? And kurtosis, in this case, it is 3.34, which is greater than 3, indicates a pointed shape. So this is a pointed. You see, it is a very sharp. It is very sharp. This bell, it is very tall at the mean value. Okay. What about the normality? In this case, the result indicates that yes, this is a normal shape because these points are exactly along the red line. Okay. Let me put another example. Another example. I am going to modify the routine of the MATLAB. So let me put here. Okay. I am going to put another example. So look now how it looks like. This is different from the previous example, okay? This is different. We are going to interpret that. So let me copy the results. I am just playing with the parameters of the routine. So let me copy this. Okay. Okay. And I am going to put here the results. Paste. Okay. So look, in this new example, as you can see, we cannot claim a normality because the blue dots are not exactly along the red line, okay? So it is not normal. Not normal, okay? But let us see. Here, the central tendency. The mean value is 0.42. The medium is 0.33 and the mode is 0.10. So how do you interpret? In this case, if the mean is greater than the median, you can see here the mean is the red straight line and the median is the green line. So there is a right skew. So the skew is that this part is very flat, okay? When this part is very flat, so this means that it drops. That means that you have a right skew, okay? The opposite, if this part was very flat, that would mean that you had in this case, a left skew, okay? In this case is right, okay? Right skew here. Okay, the dispersion. The variance is 1.21 and the standard deviation is 1.10. So this means that the data is not so far away from the mean. So if you see, all the data is concentrated around the mean, so it is not very far away. So that's That's good because all the data is concentrated. In artificial intelligence, you are going to look for small variances. What you want is small variances because if you have large variances, that means that you are not sure about the result. It could be any result, okay? It could be anything. But when you have concentrated and the variance is small, it is a good indicator that you are performing okay in artificial intelligence, okay? In terms of the shape, okay, skewness, in this case is 0.78, which is greater than 0, though that indicates a right leaning tail. Again, the tail, imagine a horse, a horse. The horse has its tail at the very end, okay? That tail, that will be like a horse tail, okay? This is like a horse tail. So you remember that when the tail drops to the right, it is called uh, right tail, and the skewness is positive. And the kurtosis, in this case, is 4.10, which is greater than 3. That indicates that we have a left kurtic shape, so it is a very sharpened shape, okay? And finally, the result of the normality test, this is not a normal distribution. As you can see, this is not normal because it has got a tail. And let's see a last example. Last example. I am going to put it here. And I am going to modify this. Okay. Okay. So let me copy the figure. Okay, here we go. This is a different distribution. Once again, it is not normal, and we are going to interpret that. Okay. I'm going to put here the results. Okay. So look now. Now the tail is on the left, okay? Let me see if I can put here. You are not going to forget this. I am going to put here this. Okay. I am going to put here this. Don't be surprised, okay? Okay. You know this girl, right? You know this girl. This is our president, Claudia Sheinbaum, okay? And she has got this horse tail. This is the name, okay? The horse tail, okay? So imagine that this is the tail, and that resembled this, okay? That resembled this. And let me put here another example. Let me see if I can do something. Uh, 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 uh. How can I have a mirror of this image? Let me see. Let me see if I can do it. Okay, let me see if I can do it. Oh, oh, oh. Mm, mm, mm. I am going to 180. Let me see if I can put it here directly. 180. Yes, I was able to do that. Okay, that's it. So look, this is Claudia Sheinbaum. This is the haircut of Claudia Sheinbaum. This is the horse tail. This is the horse tail, okay, of Claudia Sheinbaum. And here, this different is the Claudia Sheinbaum is here, okay, in this part. It is on the left hand side, okay. Well, let us see at the analysis. So the central tendency, you have the mean value of 2.45 and the median value of 2.49, and the mode in this case corresponds to 2.40, and interpretation. Okay, if the mean is greater than the median, there is a ratio. This is not true in this case. Look, the mean is not greater than the median. It is exactly the opposite. So instead of right, it will be left. So let me put this the opposite. So it is left. Okay, this is the left. You see the left. This is the left skew. Okay, that is the meaning of these values. Okay, dispersion. Variance 0.57. Standard deviation 0.76. So the interpretation indicates how far the data points are from the mean. So they are very close from the mean, you see? Look, most of the data, most of the values are very close of these two, the median and the average, the mean. Okay, that is the meaning of these values. Number 3, shape. In this case, the shape is negative. So again, Skewness is the right in the this is it is not greater, it is less than zero. Instead of right, it means left. It is exactly the same thing as the Claudia Sheinbaum horse tail. And kurtosis is 3.20. It is it is greater than 3. So that means that it is a sharped shape. You can see here. It is very sharp. Okay. Okay. Normality test. These are not normal. These values are not normal because you can see they don't align to the straight line in red. So the points have some difference here. You can see here there is some difference between the blue points and the red line. Okay, perfect, perfect. Okay, do you have any questions so far? Okay, so we are going to explain the interpretations of these variables. So that will be here in number 5, which is statistical parameters. So the mean is the average distance, which reflects the performance level. So that means that if you have a good mean value, the car is performing okay. If you have a small mean value, that means that the car is not performing so well. The variance is related to the consistency of the car. If you have a small variance, that means that the car is very consistent. If you have a large variance, that means that the car is not so consistent. Okay, so let's see here. High variance is equivalent to an unreliable design. So if the variance is so large, that means that it is not reliable. You cannot rely on this design because sometimes it will get short distances, some other times it will get large distances, and some other time it will get medium distances, and so on. In contrast, if you have a small variance, always either small distances, always small, always small, always, or always large, always. Imagine your degrees, right? Your evaluations. There are some people that it is very consistent all the time. They are very formal people, and they always get 10 as a final degree in some class. Okay, 10, 10, 10, 10, 10. But there are some people that are not very constant, and sometimes they get, for instance, in physics they get 6, in mathematics they get 8, and then in statistics they get 10. So the variance is very large, and you cannot you cannot predict what is going to happen next. In contrast with somebody who is always 10, 10, 9, 9.5, 9.6 in the notes, you can predict that this person, this student, is going to get a good result because the variance is very small. So in artificial intelligence, you have to look for small variances, okay? What about the skewness? That represents few extreme results. And that means instability. So look, the skewness, a few extreme results. This is a skewness. So you have these extreme results, but they are very few. So just some of them, very few. Okay. Here in the tail. Again, you have extreme results. These are outliers. These can be considered as outliers. They are out of the expected, right? So, but there are very few. That is the meaning of the skewness, right? Okay. Let us now talk about the number six, the sampling theory. And we'll start talking about the law of large numbers, which acronym is LLN, okay? So, if you test only 2 runs, that is unreliable. You cannot rely on only 2 runs. But what happens if you test 30 runs? You can get a stable mean. If you test 1,000 runs, you can have something reliable. You are sure that the mean value is probably this value. We are going to see in the following class some confidence intervals, right? But for the time being, now you just keep in mind that in terms of the law of large numbers, the more the better. In this case, it applies, right? The more the better. If you have more runs, it is better. It is better because you can have a better prediction or a better model. Okay. What about the central limit theorem, which acronym is CLT? Okay. Even if results are irregular, the average becomes normal. That is the statement of the central limit. Basically, the idea is that at least you have to have 30 different runs in order to see normality of the distribution of data, okay? And that is very important because when you have normality, you can have a, a powerful distribution because the normal distribution has been studied for so long. Uh, Gauss proposed this distribution, and we know everything about the normal distribution. If you don't have this normal distribution, you have to deal with other distributions. You can have a chi distribution, you can have a Pareto distribution, you can have a Rayleigh distribution. There are so many distributions, but the normal one is perhaps the most known, the most popular used in engineering. Okay, so that's why it is important to have at least 30 runs of the experiment that you are going to carry out in order to have this normal distribution of data. Okay, so in artificial intelligence, models learn better from averages than noisy raw data. Again, if I have only one or two runs, I cannot extrapolate that information. Okay, I have to run more and more experiments in order for me to get more information to estimate the average, the mean value, and that's it. For instance, imagine in this case, right? If I only run one or two experiments, well, I am just to have one or two values. But look here, when you have so many different experiments, you can record from the very small values to the very large values, right? But always within the range. This range, for instance, in this case, it goes from 0 to 4.5, okay? In this particular case, and the mean value is about 2.5. Okay. So there are some final questions for you to discuss in Teams, and then we are going. I am going to ask you to present your cars, okay? Your design, the cars that you designed during the holidays, okay? And here are the questions. Final questions. Okay. In the table, the question is why is 40 centimeters, which is the level arm length, not optimal? Do you remember here in this graph, in this table, you can suppose a priori that, okay, 10 gives me this distance, 20, 30, 40 will give me more. And it is not happening here. Why this is not happening? That is the first question. The second question has to do what would happen if we only had tested 30 and 40 centimeters, again of level arm length. What, what would have happened if I had only tested two values, 30, and 40. In this case, I tested 10, 20, 30, and 40, okay? But what would have happened if I had only tested two values, 30 and 40 centimeters? Question number 3. What if we avoid testing extreme values? Now imagine, instead of having tested 4 different values, 10, 20, 30, and 40, what if I avoid the extreme values and I just test 20 and 30? So I ignore 10, which is an extreme, and I ignore 40, that is the other extreme. What would have happened? Okay. So please write down your answers in the chat. You have it is 6:12. You have 8 minutes. At 6:20, we start discussing these answers. Okay. So I am going to put here that is individual. You carry out this individual. Okay. Final questions. Okay. So please, everyone, respond to these questions, and I will choose 2 or 3 of you in order to know your answer. So take some minutes, 8 minutes, to respond these questions, please. It is on the chat. Okay. Do you already have the answers? Okay, so let me ask. César Augusto, what do you think about the first question? Uh, why it will be why is 40 centimeters not the optimal length?
Because while a longer lever arm, duration of the energy release, um, and the pull is long and slow, and this has a mechanical instability,
Uh-huh.
static threshold, and mass to power ratio.
Okay, perfect. What about the second question? What would have happened if we only had tested 30 and 40 centimeters?
Um, the results suffer from insufficient variance and
Uh-huh.
the interstitial trends
Mhm.
and lack of curve mapping.
Okay. And finally, question number 3. What if we avoid testing extreme values?
This is in training phase. Yeah, well, it's okay. Or
Sorry?
in screening phase.
Ah, yes. Uh-huh. Yes, 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 yes.
Okay. The model for the representation trained only on safe or middle data
Uh-huh.
is from, and it cannot predict failure. And the extreme values are required to calculate the main effect of a factor.
Okay, perfect. Okay,
And
thank you, thank you, thank you very much. Well, look, here, let me go back here. Okay, I am going to take a photograph of this image, and I am going to send it to the WhatsApp group. Okay, so let me see. Experimental design. Okay, so let me take a photograph. Ideas. Here we are. Okay. Okay, you have this experimental design table, and I am going to share quickly the MATLAB. So share. Look, based on that table, you can see that we have four different experiments. The lever length, the lever arm end, it is 10, 30, 10, 30. So I am going to put this in this experiment here in the MATLAB, and the other is the string, which is 50, 50, 150, 150. Here, these are the input data, the independent variables, and the dependent variable, which is the distance. It is from the table 4.2, which is here, 6.8, here is 9.1, let me put 9, and 9.5. Okay, so let me run this. Okay. Okay, and I am going to share the result, okay? Here is the result, right, of the table that I just shared in the MATLAB. So let me put here. I am also sharing the this graph in the WhatsApp group, okay? Okay. And let me put here, and we will interpret that. Okay. So look, I have only just 4 experiments, okay? 4 experiments. The first experiment, I have got the lever, which is 10 centimeters, and the string, which is 50 centimeters, and the distance is 4.2. Okay. Then I have a second experiment based on the table again. The second experiment, it is 30 and 50. Okay. So the second experiment is this one. You have the lever arm is 30 and the string is 50 and the distance is 6.8. You can see these 3 points. Then I have a third experiment, which is now the lever 10 centimeters and the string 150, and I can reach a 9.1 distance. And finally, the fourth experiment is 30 for the lever arm, 150 for the string, and the distance that I can reach is 9.5. Okay, so if I had more experiments, I could have not a flat. This is a flat shape, okay, but a curved one, right? I could have a curved shape of this experiment, right? And the curved can reflect the these optimal points, okay? Because here the optimal point, the maximum is located here, right? When you have 30 in the lever, 150 in the string, and the maximum distance is 9.5, okay? But again, these are just a few experiments, so I need more experiments. So with that, I can conclude the following. Here we are. Let me put here. Uh, uh, uh. These are going to be our conclusions. So let me just write it down for you in the file. Here, okay. I have already put this figure in today's lecture notes for you to have. Let us put the final conclusions. The conclusions, okay? Conclusions for today. Bullet points. So first, if you have poor sampling, you are going to have a biased model, okay? So that's why I was telling you about you have to increase the runs in order to have more data to make it more reliable, your model. Another thing that you should keep in mind is the high variance translates into unstable predictions. If you don't carry exploratory data analysis, you can get to wrong conclusions. And once again, in artificial intelligence, interpolation is safe, but extrapolation is dangerous, okay? Okay. Here we go. Okay, so let me I am going to share this with you. Okay. Okay. Well, how was your experiment, the mousetrap experiment? Was it okay? Was it easy? Was it hard? Who can tell me how was your experiment at home?
It was fun.
It was very fun, right? Yes, yes, yes. It has happened. I usually put this exercise in some of my master students' class, and they have a lot of fun when they are doing the experiment. Okay. Okay. So let us see. I am going to share as well in the WhatsApp. Here is the lecture note for today. Remember, we are using Dr. Sala's book, The Experimental Design for Artificial Intelligence Engineers. This is our textbook, let's say, right? And we are now in class explaining the concepts and things like that, carrying out some exercises and putting some examples forward in order for you to better understand the concepts. But all the theory and all the things you can find them in the book that I shared at the beginning of the term, right? Okay. So who wants to present his or their car? So let me see. Who wants to present the car? I'm going to put here. I am moving this camera. Okay, so I am going to share my screen. Let's go to the mm, mm, oh, it's frozen. What happened? What happened here? Let me see. Share. Uh, 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 uh. Okay. I don't know. Let me change the computer. Okay. 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 Let us ask Daniel Aguilar. Are you there?
Yes, teacher.
Okay. I am going to share your project on the screen. Will you be so kind, please, to tell us about your experiment? So let me just find the calendar. Here we are. Okay, okay, okay. Mm, here, okay. So let's go to the Teams. Okay, okay. So here it is the mousetrap design. Okay, what can you tell us about it? Can you hear me, Daniel? I think that your microphone is closed. Uh, can you open your microphone, Danny, please? I can't open. Okay. Who else is in this team? Daniel, Ebony Alexander, are you there? Ebony is getting inside. No, no yet, Danny. No, we can't hear you. Or Alan Moreno. Is Alan or Luis Ángel? Luis Angel, are you there? Ebony? Uh, okay, well, let's see another team. Axel.
Yes, teacher.
Okay. Can you tell us about your experiment, please?
Mm, yes. Well, mm, the results of our mousetrap car design. Mm, our main objective was design, build, optimize a mousetrap car,
Uh-huh.
and to power to travel the maximum distance. To do this, we didn't just use trial and error. We
Okay.
applied the principles of experimental design. We
Mm-hmm.
tested three dependent variables: the lever arm length, the string length, and the chassis weight.
Okay.
During our screening phase, we discovered that the lever arm length was the most influential factor on the car performance. So we insulated it for the next stage.
Okay. These were your
Um,
distances, right? Recorded.
yes,
Okay. But you here you missed some combinations, right? For instance, short, heavy. You missed short, light, ¿verdad? Then long, light, short, long, length. Okay, but it is okay. Four experiments. Okay.
yes,
And this is the maximum distance that you could record, 1.10 meters. Yes.
yes, teacher.
Okay.
And with the four different legs of the lever,
Hmm.
we found a short arm of 10 centimeters, act like a first gear in a car.
Hmm.
Here the lever is a violent initial torque that causes wheel spins and traction loss. On the other hand, 40 centimeters arm is too long, exceeds the structural limit and loses elasticity efficiency. In theory, our
Hmm.
optimal configuration was 30 centimeters.
Hmm.
This leg acts like a progressive gear, distributing the energy in a sustained manner and maximizing the mechanical efficiency. With the setup, we achieved the maximum distance.
Okay, and it was 1.16 meters, right? This is the maximum distance that you could
Yes,
that you could get. Okay, okay. It happened something very similar, right? What we saw in the lecture today in this graph.
sí, similar.
Okay, okay. So your final optimized configuration would be 30 centimeters in the lever arm, the string 150, and the lightweight chassis. And this is the maximum expected distance. Okay.
And about the artificial intelligence, first, if we only train an intelligence model with good designs, the model suffers from statistical bias. It needs to learn from failures to map the system correctly. If
Okay.
we don't test the extreme case, the AI will fail.
Okay. Okay, perfect. So this is the car, right? Was it
Yes.
difficult to get the materials, or you already have at home these CDs and all the things?
Some CDs, I have some, but not the four, and was little difficult to find. But
Okay.
the rest was easy.
Okay. Okay. Perfect. Thank you. Thank you very much for the presentation. Okay. Thank you, Axel. Let's go to another team. Juan Carlos, are you there? Juan Carlos Charbel?
Yes, I'm here.
Okay. What can you tell us about your mousetrap card design?
Can you repeat, please? My internet is
Yes.
está fallando.
Can you tell us about your design explain?
Well, it's a car make by different materials like mousetrap and four CDs
Okay.
and a wooden stick. The car, el cuerpo del carro,
The chassis.
it's made by a, a- a un pedazo de cartón
Okay. Board. Okay.
and the edges of these wheels
Axles
is like
of the wheels.
popotes, no sé cómo se dice en inglés, pero
Strip. Okay.
yeah, thanks.
Okay. So it was
And
very light.
yes,
Okay. These are the variables, right, that you considered.
yes.
Okay. How were your results? What are your results? String. You carry out the experiments independently, or you make some combinations of these variables. Is there anybody else from this team? Let's look. Angel, are you there?
Yes, teacher, I'm here.
Okay. Did you make some combinations of the variables, or just first you tried with the lever arm and then you tried with the string length?
Yes, we tested some different combinations. We changed the length of the lever arm. We also tested the wheels without synthesizer. I don't
Yes,
know how
yes,
to
yes.
say that.
The rubber. Okay.
Yes. We well, in the first photo pictures, you can
Uh-huh.
see that the mousetrap is glued to that piece of cardboard, but
Mm.
in other experiments, we added an extra part of cardboard at the end. So
Okay.
we made the lever arm longer in
Okay.
order to make the car able to uh, run a
Go
longer
farther, no?
distance. Yes,
Okay. Okay.
uh, that's what uh, that's what well, eso fue lo que hicimos.
Okay, that's what you did. Okay.
Yeah.
Okay, the 2 point here you can see again, right? That the if you increase the lever arm, not necessarily means that you are going to increase the distance, right? And this is your practical results, okay? Okay, so what is the optimal configuration?
Well, as you can see, the lever arm is 30 centimeters and the string length is 150 centimeters with
Okay.
a light chassis.
Okay. And you can reach theoretically 7 meters, right?
Yes, more or less.
Did you try it? Did you? This is the
Yeah,
optimal design. This is the optimal, right?
that's not the final
The final design.
design.
Let me see.
We have a video actually.
Do you? Is it here in the Teams? No.
No, I think that my classmate Debbie didn't share with us the video.
Debbie, can you share the video? You share your screen, and I stop sharing.
I don't know if she had the video with the best experiment, but
Okay.
she had a video. She have
Ah,
video. She
okay.
has.
So some video. Debbie, do you have the video?
Yes, teacher.
Can you share it, please?
Sure. Wait a
Okay.
minute.
Okay. Okay.
Can you see my?
Screen, yes.
Yes. Okay.
Okay. Perfect. That is the optimal design, right?
Mm, yeah, maybe. Fue lo que se nos
Oh,
ocurrió.
oh, oh my God! It's going to Acapulco.
Exactly.
Wow! How far it get? It is like 20 meters or something like that, right?
But
Did you
my
measure that or not?
no, no lo medí, la verdad.
Okay. But do you have the car, right, with you?
Yeah, yeah, with me
Okay.
I home. Pero estábamos comentando que tal vez con un diseño tal vez un poco más amplio, de algunos centímetros más grande y un palito de palanca más grande, podría recorrer aún más.
Okay. How did you manage to avoid because when you put the cord right in
Yes.
the axle,
Ah,
it happens that the mousetrap freeze, but it suddenly stops the car. How did you manage to keep the wheels running, the wheels running?
no sé si
That
le entendí,
that's
pero lo
interesting.
pusimos como, bueno, es que no sé cómo decir en inglés, le pusimos como un palito para que se detuviera ahí.
Okay,
Este, bueno, sí, en parte sí usamos popotes para fijar hasta un
Lo-
cierto punto, bueno, un centímetros exactos cada rueda y así no tuviera esa como que una desviación. O sea que sí se mueve en recto.
okay. That's very creative and interesting. Okay, I would like to see the car. I would like to see the car. Well, all the cars. Okay. Okay.
Ok.
Well, guys, thank you very much. The following week, we are going to start with the remaining teams. Okay. Don't worry. All of you are going to present your mousetrap. Okay. But for now, we are going to stop here the lecture. So I am going to stop recording. Wait a minute, please. I am going back with you. Thank you so much, everybody, for your presence.